and when, and, you know, take a step back, and we are going to do some of the math that we skipped at the beginning of the course. As I've said before, there's really two ways that I can think of to teach the class. One is that you do a lot of math at the beginning, and then you start to solve problems later. Or you can start to solve problems and make a few assumptions, and then you can fill in the math sort of between exams, where it's important for people to see the math, but it's also important to get people solving problems, I think, a little bit earlier. So we've done that. You know, the first almost 20 lectures and the course material that's gone along with that has focused on getting you comfortable with solving problems. And so now that we're in this lull between exam 1 and exam 2, I'd like to go back and fill in some of the math. And to do that, I want to start our discussion all the way back to our first law. And of course, the first law of thermodynamics states that the total energy of any system and its surroundings is conserved. And most people say that means, well, energy can't be created or destroyed. But the key for me in this first law is, since you have to conserve the energy of the universe, what that means is that energy can be transferred between the systems and the surroundings as heat or work. And for a closed system, you know, that has led to us to write things like delta U is equal to Q plus W. And so we know that, you know, also within a system, we can convert energy from one form to another. And so, you know, maybe a better understanding of that is in the open system energy balance, where we know that that's Q plus W plus the sum of the enthalpy that's entering the system minus the sum of the enthalpy that's leaving the system, plus 1/2 times the mass flow rate times V in squared minus V out squared plus m dot times the gravitational constant times the change in the height. And maybe the reason that that makes a little bit of sense to us is that it goes back to what we've learned in physics, that you not only can have changes in energy that are thermal or chemical, right? Because that's really, this is what we think of as thermal. This is what we think of mostly as chemical changes. But you also can have things like exchange between the kinetic and the potential energy of the system. And so some of these things, I think, make a lot of sense to us. But something that we've talked a lot about during the course of our semester that is really hard to really think about what it is the internal energy. And I think that the difficult part of understanding the internal energy is for us to step back and to ask ourselves, when we exchange energy between the system and the surroundings, and the system either accepts energy or gives energy, what is really changing? And if you remember the way that we derived the heat capacity for a simple monatomic ideal gas, we made a very simple assumption, was that first that we have the kinetic energy. And in fact, when we derived the heat capacity for that simple monatomic ideal gas, we only considered kinetic energy, right? And we really only considered motion. But we know that if we're going to think about this, there's multiple types of kinetic energy, right? So of course, motion is one of them. And can you guys think of a couple other ways that you could store kinetic energy?
You can have rotational kinetic energy.
Yep, that's right. So you can have rotation. And there's one other one that I'm thinking about. Can anybody maybe think of it quickly?
Heat?
Now,
would it be vibration?
Yeah, it's vibrational energy, right? And for a monatomic gas, a vibrational energy doesn't make any sense. But now all of a sudden, if you have oxygen, which has a bond between them, we know those bonds vibrate. And remember, that was actually one of the reasons why when we considered simple diatomic gases, that the heat capacity increased, because now suddenly you not only store energy by motion, but you also have vibration. Then triatomic gases not only add different modes of vibration, but you also can have different modes of rotation, and those get more and more complicated. So we know that we're going to store energy in the system as kinetic energy. But we also know that we're going to store energy as potential energy as well. And there's really two different ways that I think of potential energy in a chemical system. So does anyone want to come in and give us maybe one of those sources of potential energy?
Isolation columns? Or am I thinking too advanced?
Yeah, I think, you know, we're at the molecular level, right?
Okay, okay.
So at the molecular level, how might we think of there being potential energy?
Could there be like potential energy in chemical bonds?
I think the breaking of those bonds will have energy related to them. So that's not exactly what I was thinking of, but there will be some element of that in a system. But I'm still thinking, you know, let's just take a simplified system that has one gas in it, right? So there probably wouldn't be reactions. So how could we change, or how could there be potential energy in that system?
High heat, like if you store steam, the water molecules tend to like vibrate a lot.
But vibration is in our kinetic energy. So you're right, they would store energy, but through vibration, right, which is kinetic. So the most obvious one perhaps is that the height can change, right? But the one that's more important for us is that molecules, when they get close to each other, they interact. Where if two oxygen molecules get too close to each other, they will repel each other. From a far distance, they actually attract each other. If one of them is charged, there's electrostatic interactions between them, right? So we're talking things like the weak nuclear force, the strong nuclear force, right? Electromagnetism. And so these are some of the things that you learned about in physics that, you know, we will generalize as just molecular interactions, right? That can take any of those forms. And you might even remember that you had two objects separated at a distance in physics, and they said, look, you know, there exists some well where, you know, here you're strongly repulsive, here you're attractive, and then you get to the bottom of this well, and then you sit next to each other, right? So hopefully that rings a bell from physics or from a chemistry class that you've taken in the past. Now, in physics, you get a lot of problems that has a ball dropping from a known height, or maybe in some of the more straightforward applications of this in physical chemistry, you have two atoms or even two very simple molecules that exist. And it's very easy to account for the motion, rotation, vibration, and potential energy when you have a very simple system like that, where you just have one object or maybe two objects. But I want you to look around the room that you're in. How big is that room? And if we assume that the air in that room behaves as an ideal gas, which it should, we're way above the critical point, the critical temperature for oxygen. Well, 1 mole of oxygen is 22.4 liters. And if that number doesn't have meaning to you, that's like 0.8 cubic feet. And just at 1 atmosphere, 1 mole, room temperature, we have 6.022 times 10 to the 23rd molecules, right? This is Avogadro's number. And the room that I'm in is about maybe 12 feet by 14 feet by 9 feet. So, we're talking many, 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 many cubic feet. And so, yes, it's easy for us to track the motion of one thing. But given the space that I'm in, I can say, well, I'm going to estimate there's about 10 to the 25th molecules in this room of just gas. And then, of course, I'm sitting at a desk and I'm sitting on a chair and there's books and a bookshelf and there's me. I mean, there's many, 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 many molecules, right? So if we take the system of the room I'm in as just the air, and I'm happy to be part of the surroundings, I guess, there's 10 to the 25 molecules in our system. This is a huge number of actions and interactions to track. In fact, it's an impossible number of interactions to account for. And if you want proof of that, just Google some of the most advanced work on molecular dynamic simulations. They're really super interesting. But you'll notice we now can accurately model the motion of maybe thousands of atoms, maybe hundreds of molecules. So there's no way that today we could model 10 to the 25th molecules accurately. And there certainly was no way to do that at the birth of thermodynamics, which was over 100 years ago. And so what we needed to do was to find a way to account for all of these interactions in a relatively straightforward way. And so the real first step that you would take in generating the field of thermodynamics is you have to assume that some things are true. And when you assume that something is true, right, we say that you're postulating, right? So you can come up with postulates. And from those postulates, you can then develop all the math that we need. And so postulate 1 in thermodynamics is that the energy of a system can be completely characterized by a quantity called the internal energy. And that's given the symbol U. And that quantity is perfectly described by the number of moles in the system, the size of the system, and its arrangement, right? Or the number of moles, the volume, and the entropy. And mathematically, we can say then, right, this internal energy, which is just a bulk quantity of all of the interactions that we've talked about for all of the molecules in the box. And so we can say then, we know that the internal energy is a function of how these molecules are arranged. Or remember, the entropy is actually the number of possible arrangements of the system times the volume, or not times, sorry, but it's a function of the number of arrangements, the size of the system, and the number of moles. Or we actually can write an intensive version of this as well that just says the internal energy is then a function of entropy and the specific volume. Okay, and the thing that we mean by this is really that, you know, this concept of a canonical independent variable for our internal energy are S, V, and N. And what that means is that if we know the entropy of the system, the volume of the system, and the number of moles, not only do we know the internal energy, but we know all possible thermodynamic information. We could calculate the temperature. We could find the pressure. We could find the chemical potential. We could find all these other things if we knew that function. Okay, and there are some really interesting things about this, and there are some complicating factors that we're going to talk about during our lecture today. But I want to start with this expression for the internal energy, because we're saying that we could know the internal energy given S, V, and N. And if you remember, that led us early in the semester to think about changes in different variables as a function of their key variables, right? Really from a Calc 3 perspective. And we were able to then say, well, how does this value change as a function of those variables? And if we were to think about it that way mathematically, we then could say, well, the change then in this thing that we call the internal energy is actually just equal to the change. Here, let me be very specific about this, that's equal to the change of that variable as a function of its canonical independent variable. And you have to hold everything else constant, right? So this is at constant volume, at constant number of moles of everything in the system, times the change in the entropy, plus how this variable changes as a function of volume at constant entropy and the number of moles times dV, plus the change in the internal energy over the change of the number of moles of one of the species at constant entropy, volume, and all of the other species in our system. And the interesting thing from here is that we actually should know from our experience in this semester what this one is. Does anybody want to venture a guess what that differential is, given what we know about maybe our expression for work? So what is normally in front of our dV in the work term?
Pressure?
Yeah, pressure. It's minus the pressure, right? And it turns out that this is the mathematical definition for pressure. So pressure is minus du dV at constant S and N. While we're looking at that, so when we think about our entropy balance, what are the variables that are really in that balance? I know we have delta S of the system, we have SG, we have Q, but what's the only thermodynamic variable other than entropy that directly appears in the balance?
Either Q or temperature of the surroundings, right?
Yeah, so remember though, Q is not really a thermodynamic variable, right? It's a measurement of the amount of heat that's been transferred. But the temperature is absolutely correct. And there's this relationship that exists that we get a feeling for throughout our course, where temperature and entropy are always somehow related, because even we know when we generate entropy, that often means we give off heat, and we at least think of heat as being synonymous with temperature. And so this first term here is the thermodynamic definition for the temperature. So the temperature actually is defined thermodynamically as the change in the internal energy as the entropy changes when you keep the box and the number of moles the same size. So it's du ds at constant V and N. And this last term, if we have multiple components, right? So it's not just this one N, but it's actually, if you think about it, we've used this before in our class, that it's actually the sum of all of those. And for any one species, this differential, so du dni, or the change in the internal energy as you add or remove things from the system at constant SV and all the other stuff, right, is actually just defined as the chemical potential for species I. And so if we look at it this way, the differential for you is just equal to TDS plus or minus PDV plus the sum of the chemical potential of species I times the change in the number of moles of that species. Or if we have a single component system, or if we don't have any change in the composition and we want the intensive form, we also can write that du is equal to just TDS minus PDV. And this is a differential. And one of the really interesting things about having a differential, and it's the reason that I said that S, V, and N were these canonical variables where we could know everything else. Because if we knew a function for u, well, if you think about it, if we knew the function for u and we knew entropy and volume, if we took du ds at constant volume of that function would be equal to temperature. And then we could plug in the variables that we know and actually calculate the temperature. Or if we had that function, we could take du dv at constant entropy and plug in the variables that we know, and that would be equal to minus the pressure. And in homework 6, I'm going to give you guys one problem where you guys will practice doing exactly this. Because you've probably never before in your life seen a function where u was actually equal to some really long function of the temperature and volume. The entropy and the volume. And if you did, this would be called a fundamental relation. If you had u as a function of S, V, and N, that would be a fundamental relation. And before we finish lecture today, I will show you an example of the fundamental relation for an ideal gas. So you know what they look like, and you'll know what to expect when you're going to solve a problem based on that. Okay? So before I move on, and we're going to do a little bit more math, does anybody have pressing questions about what we've done so far?
On the left for T,
Right above fundamental relation, the du ds, is that d mu, like the chemical something you said, or is that
Nope.
du?
Yeah, sorry.
Okay.
Thank you. That is du. Yeah, great
And then could
question.
you also explain the thing that's represented by mu again? I didn't really
Yeah.
follow that.
No, that's a good question. So this is actually the definition of the chemical potential. Which you guys will use the chemical potential a lot in Thermo 2. And it actually turns out, and we'll show you this in a minute, that actually the chemical potential, even though you can get it from du, the chemical potential is essentially equal to the specific Gibbs free energy at a known temperature and pressure. And we'll do some of the math to show you that in a minute. And that'll be the key, because you guys have probably heard before that the uncontrolled variables of the system arrange themselves to either maximize entropy or to minimize the free energy. And you will use that in Thermo 2 when you talk about phase equilibria, because if that's true, you actually know that the chemical potential of multiple phases in equilibrium with each other have to be equal. And because of that, the Gibbs free energy becomes a very, very helpful tool to use to then solve those problems where you have to talk about what happens at the interface between phases. But I don't want to put the cart before the horse, right? We don't need to do that this semester while we're still getting a grasp of the fundamentals, okay? So we have this definition for something that's called the internal energy. And we've made assumptions about its canonical variables, right? We've postulated that if we know the entropy, the volume, and the number of moles, we would know what the internal energy is. But there's an intrinsic problem from a practical perspective with this definition, because we could use statistical thermodynamics, which probably is like 4 thermo classes from now, and we could understand really what entropy is, and we could find sophisticated ways to determine the number of possible states. But entropy is not a readily measurable variable. From the third law of thermodynamics, we can always calculate what it is, because we have a standard definition for absolute zero entropy, right? But it's not possible for us to do that calculation in a general way for all systems, especially with this number of components, if you think about what we'd actually need to do. So instead of doing that, we still want a bulk energy that we can use to talk about physical changes, but one where we don't need to know the value of the entropy. And so what we're going to do is we're going to do a mathematical transformation. And so, we're going to come up with an energy that transforms this entropy value into something that we can measure, and that's the temperature. And so to do that, we're going to have a new definition. So we know from above that du equals TdS minus PdV. But now we are going to define a new quantity that's called the Helmholtz energy. And we're going to say that A, which is the symbol for the Helmholtz energy, is just equal to U minus T times S. Or we also could do lowercase a is equal to U minus T times S, right? So the top version is the extensive, the bottom is the intensive version. And As we do this, I'll also tell you that sometimes the Helmholtz potential is not described by the letter A, but also could be the letter F. And that's done because we also use area in our calculations. And so in especially beginning thermodynamic calculations, F is oftentimes more, it's easier to use. So you make sure that, in some first law problems where the velocity changes, for example, you wouldn't have to confuse the Helmholtz potential with area. Now, of course, every letter in the alphabet's already been used. So it turns out if you do a lowercase script f, that's also fugacity, which you'll learn about in Thermo 2. So you may or may not like that one. And capital F is also Faraday's constant, which is essentially the charge per mole of electrons. And there are also fields where this would be a conflict. So we're going to do what your book does, and we're going to use A. But just for your information, it also can be F. So if we look at this and we say that A is equal to U minus TS, well, if we take the differential here, that means that dA equals du minus d times T times S. And we know from our relationship that we had above, right? So dA equals, and we'll insert what we had for du. And du was TdS minus PdV. And then that's minus dTs. And so that means that that's TdS minus PdV minus TdS minus S dt. I'm just going to be sure to be clear that we're doing the intrinsic form here. And of course, those two cancel. And so we find that dA, or the change in the Helmholtz energy, is equal to minus S dt minus PdV. And the Helmholtz energy is not actually used a lot. It is minimized at a given temperature and volume. One of the interesting things about the Helmholtz energy is that its change is equal to the work done if the process is done at constant temperature. So if you think about this, at constant temperature, then you would have dA equals minus S dt minus PdV. Well, at constant temperature, that's equal to 0. And so the change in the Helmholtz potential would be minus PdV, which we've already said is the PV work that you could do in a system. And because of this, it's often said that the Helmholtz energy gives you the maximum useful work that is possible. Okay? And if we look at this differential, remember the canonical variables for the internal energy were entropy and volume. Well, now what we've done is we've made the canonical variables for the Helmholtz potential temperature and volume. So what we have is, or what we would like to have, is the Helmholtz potential as a function of T and V, or T, capital V, and N. And one of the interesting things to me is that although we don't use the Helmholtz potential a lot, we actually use enthalpy and the Gibbs free energy the most. And for closed system problems, we do use the internal energy. But despite the fact that it's not readily used in courses to solve problems, it turns out that most of the fundamental relations that you can get from statistical thermodynamics it's much easier to derive them as the Helmholtz potential. But that's okay, because remember, if we ever wanted to get back to the internal energy, remember that A just equals U minus T times S, right? Or U equals A plus T times S. And so if we had this fundamental relation, which is the Helmholtz potential as a function of its variables, we actually could always get back to the internal energy by applying that equation and make substitutions for our definition of the temperature. And then we would get the internal energy as a function of the entropy, the volume, and the number of moles. So like I said, you guys will have one problem in the next homework assignment where you're going to do some of these transformations just to practice the math and to have seen it and to have done it once. But we're not going to do an extensive number of these this semester, okay? So here we have this Helmholtz potential, right? We have, which is now also, oops, sorry, I'm actually bracketing the wrong thing. So we have a second differential, right? So we boxed the one for the internal energy above. Now we have one for the Helmholtz potential. Now another potential or another energy that we find very helpful in thermodynamics is enthalpy. And it's really born from the fact that we don't necessarily measure volume very well either. So we can define the enthalpy as being equal to U plus PV, or U plus P times little v. And if we do the same thing that we just did for the Helmholtz potential, well, dH is equal to du plus dPV. And so dH then equals TdS minus PDV plus PDV plus VdP. And those two cancel. And now we have a differential for the enthalpy, which is equal to TdS plus VdP. Okay. And now this doesn't necessarily get us around the problem that you can't measure the entropy, even though we do use enthalpy all the time. So sometimes what we want to do then is then further transform the enthalpy into the two most commonly and easily measurable variables that we have, and that is temperature. So we can get the Gibbs free energy from H minus TS, right? Or H minus TS. And if we wanted to, we could expand this, right? This is just U plus PV minus TS, right? Or U plus PV minus TS. And so if we just take the differential for the Gibbs free energy, so then dG equals dH minus D times TS, right? And so then dG equals TdS plus VdP, which is the differential we had above, minus TdS minus S dt. And these cancel. And we have our fourth differential, that dG is equal to VdP minus S dt. Okay. And so we have four energies that we're going to take into consideration, and we will have, so we have four differentials. If we wanted to, right, if we had a function, right, so this means that for enthalpy, the canonical variables are S, P, and N. And for the Gibbs free energy, the canonical independent variables are pressure, temperature, and N, which of course, as I said, are much easier to measure. So if we had G, a function for G as a function of pressure, temperature, and the number of moles, we could find everything else, right? Because we could find the volume, right? Because the volume would just be the differential of that function at constant temperature, right? You could actually find the entropy, which would be minus the derivative of that function at constant pressure. And then we could get to all of the other energies from these types of transformations, which is actually really useful. And we can then, we can do that and manipulate our equations and systems depending on what it is that we look for. Now, of course, in our course this semester, we're mostly going to use the internal energy and the enthalpy. And as I said, in Thermo 2, where you think and talk more about multi-phase systems, that's where the internal energy comes in handy. So one of the things then that I wanted to point out that we can use the differentials for is actually maybe to even slightly better understand some of the variables that we've looked at, or alternate definitions for variables that we've already looked at this semester. So let's ask ourselves, what is the change in the internal energy as a function of temperature at constant volume? Okay. Well, we know that du is equal to TdS minus PdV. So du dt at constant V just equals T times ds dV, or sorry, dt at constant V minus P times dV dV, or dt at constant volume. So what's dV dt at constant volume? What's that equal to?
Would it be 0?
Yeah, exactly, because dV would be 0, right? So that thing is equal to 0. So that means that du dt at constant V equals T times ds dt at constant V. And does anybody remember what we actually called that a few weeks ago? I just asserted that it was true, but now we're actually going to sort of derive it. So this is asking, how does the internal energy change with temperature, right? So if I were to write this equation, du for an ideal gas equals what? What would you tell me?
dq plus dw? Or are you looking for something else?
Well, dq plus dw is correct, but let's say I wanted to actually find the value. What equation would I put in there? Du would be equal to what?
TdS minus PdV.
Not the differential, but something that we've used a bunch this semester in solving problems.
The integral of CV, is that what you're looking for?
So remember, so delta U would be the integral of CV times what? dt. So yeah, that's right. So this would be, so we haven't integrated it yet. So du is equal to the integral of CV dt. So if I took du dt at constant V, that equals CV. And this is where this equation actually comes from, because the mathematical definition of the heat capacity is T times ds dt. But if you look at what we did today with the differentials and how we can define the temperature, well, from this equation right here, we get that du, right, dt equals CV, or du equals CV dt, right? And so that relationship that we've been using this entire semester comes naturally out of the differentials that we were talking about today. And we could do the same thing with the enthalpy. So if I said dH dt at constant pressure, well, we know that dH equals T times ds plus VdP. So then dH dt at constant P equals T times ds dt at constant P plus V times dP dt at constant P. And of course, just like the previous example, right, that's 0. And so now we have a relationship that dH dt at constant P equals T times ds dt at constant P, which we talked about several weeks ago is actually the constant pressure heat capacity. And from here is also where we get that dH equals Cp dt. Always. Because we've always taken that derivative under a certain condition of constant pressure. And it's an actual formula. It's a mathematical equation that you take the derivative of and you get another function from it. So as I said, I don't want that to be unnecessarily confusing today. And so I'll give you guys practice doing that in one of the homework problems in homework 6. So what I really like for you guys to take away from lecture today is how we've had to postulate an arbitrary function that summarizes or sums all of the interactions between the trillions and trillions and trillions and trillions of molecules that are in the space around us. And we've arbitrarily named that the internal energy. And then we believe that we know, or that we can summarize that energy if we know how it's arranged, what size the box is, or what size the system is, and the number of components inside of that. And from there, we have sort of transformed that postulate into different differentials and defined 3 other energies that we're going to use: the Helmholtz potential, the enthalpy, and the Gibbs free energy. And in our next lecture, we're going to use those 4 differentials to do something that I think is pretty interesting and to prove things that we said were true at the beginning of the semester. For example, for an ideal gas, dH is only equal to Cp dt, which is boxed here. But that's only true for an ideal gas. And we'll show you why next time. And then we're going to end up with, so we have 4 new equations from today. We're going to have 4 new equations and relationships in the next lecture. So I'll show you how to get those 4 new relationships. And then you're going to think, how am I supposed to remember all of these things? And I'll give you a shortcut on how to do that. And if you want to look it up before then, the shortcut is actually called the thermodynamic square. Okay? And it's really a square where you can remember the order. It's very awesome thermodynamics undergraduate students have passed. And we'll teach you how to use that next time.